Hello all, welcome to our channel Way to Know. So in this video we will talk about a comparator circuit. Now comparator circuit is very simple, right? For example, let us assume this is a comparator, okay, and let us assume there is no feedback here, R2. So in this scenario, whenever example, if we apply a signal, okay, at the inverting input more than the non-inverting input, the output goes low, and when the signal is less than the supply or V reference provided the non-inverting input, the output goes high. This is a simple comparator circuit. Now the major issue with with that type of comparator circuit is what happens is whenever there is a small fluctuation near the threshold, that means near the Vref signal around of this Vref level of this V signal, there will be continuous fluctuating at the output. This scenario you can compare with the scenario like a button, where button toggles and there'll be debouncing in the button, and what happens is there'll be more of unnecessary toggling that will be happening, right? Similarly, in the comparator circuit, to eliminate any such scenarios where you want to avoid the output toggling, we use a comparator with Schmitt trigger. Schmitt trigger, what does it do? It brings a small window where when the input, that means V signal, goes above specific level, then only the um, output transitions, and then only when the signal goes below a specific level, then only a signal transitions. That means there is a supply between two levels where the comparator actually has to remain in the specific state without changing its state. So that's how a comparator works. Now, a Schmitt Trigger hysteresis works, right? So we call it VAL and VAH levels, where the difference between them, the window, is a dead zone, where if the signal is in that area, nothing happens, there won't be any toggling. Okay, so we are going to explain about that kind of circuit. So here we have used LM741. Okay, for this we have a dual supply, and the supply is around 9 volts, plus 9 volts and minus 9 volts, and we have a signal input. So the signal input is this, where you have DC offset of 0 and amplitude of 9 volts. And what we are doing is it is transitioning at a frequency of 10 Hz, very low frequency enough for the circuit to operate, and then we are giving 25 cycles. So that's the signal that is given as input. That means a signal transitions between two levels, and this is a sinusoidal wave, and this is enough for us to provide input at the non-inverting input to talk about the or to explain the window based or schematic trigger based comparator circuit. And this anyway we are doing in LTspice, which helps us simulate and get to know the results. Now that is about the signal. And now for the LM741, we can use it in a comparator mode. But if you want to have a Schmitt trigger based comparator mode, you want to add a feedback to the non-inverting terminal, which basically introduces a positive feedback, right? There is a positive feedback, and this positive feedback is applied to the terminal, and then we have a VREF also applied. That means we have output and VREF, which are actually combined at the non-inverting terminal. So now in this scenario, for this particular op amp, the output high will be plus 9 volts. That means this is what the maximum high that can go at the output of the op amp, because the positive supply is 9 volts. Whereas VOL, which is the lower voltage, is minus 9 volts actually here. Okay, so this will be minus 9 volts. Okay, so that means the signal can transition between output can transition between minus 9 volts to 9 volts based on the level of the V signal and compared with the non-inverting input. And then we need to know what are the levels at which these transitions happen. Okay, now this particular first one, if you see the first formula, okay, determines the threshold at VAL, for VAL. So VAL is nothing but the lower threshold, and when the threshold goes below that VAL, what happens is you get a positive output. Okay, because the inverting terminal goes below this particular threshold. That means the non-inverting terminal has higher voltage, and we have a higher high on the output, which is a basic comparator functionality, right? And then we have something as a threshold for VIH. And what happens is when this particular signal crosses this VIH level calculated based on this, what happens is the output goes above when the output goes above this particular VIH, okay, which is at this level, at this node, the output goes low because the inverting terminal voltage has increased. So that means we are basically designing a circuit, Schmitt Trigger based circuit, where we are eliminating unnecessary toggling at the output because of simple noise on the input terminals. That is the intention here. Now let us try to simulate this circuit. Okay, now you can see here when we simulate this circuit, okay, uh, you can see this is the input, which is minus 9 to plus 9. Okay, this is minus 9, this is plus 9. So there is a sinusoidal signal which is expected here. And what is happening here is once the signal goes high, you can see here the sinusoidal signal is going high, and when it reaches approximately, let us put the cursor around 5.5 volts, what is happening is you can see when the signal crosses this, it has gone low. That means there is a VIH level, and when the sinusoidal signal is crossing this VIH of approximately 5.5, the what is happening here, the inverting terminal is crossing that VIH, and the output will go low because the inverting terminal voltage has exceeded the non-inverting terminal voltage, and then it has gone high. It's a sinusoidal signal, right? It has gone high, and then when it falls, it doesn't fall at this VIH as we talked, because that's the basic comparator functionality, but we are having a Schmitt Trigger functionality, right? So now what happens is when it goes low, and it goes low beyond 3.3 volt, then only the output goes high. You can see here the blue line goes high. That means the inverting terminal voltage has gone below a specific voltage on the non-inverting terminal, so that the output is high because non-inverting terminal voltage is high. So that is how the comparator works, right? So that means with this band, you can see here this particular 5.5 to 3.3, you actually see that the comparator doesn't respond to the input voltage, and it remains at a fixed level. Okay, so now what we have to understand here is how we are going to change these thresholds. You can change the as we see from this formula, to put a threshold, we can change either of these. Whether you can change the reference voltage straight away to adjust the VIN and VIH, which you can see from this, which equally impacts the VIL and VIH. That means symmetrically it changes. But in case if you change, or you change VOL or VOH, like example, you have plus 9 volts but minus 5 volts here, then again the thresholds are going to change. VOL will impact the VIL value. Okay, so that's how you can play around, and you can build the circuit, use it for your applications based on the signal. And here, understand that we haven't considered what is the signal, what is the impedance parameters of the signal. We have considered an ideal signal input which has zero output impedance. That's how what we have considered here. And here also, when we are talking, the op amp output is considered zero. We are not considering its impact. It might be there in the model. You can check your model, and also the input impedance of this particular op amp is considered infinite. Okay, so these are the a few assumptions here that are considered, but at least signal is what we can include. The LM741 parameters are part of its model, but the signal related thing, in case if you want to add a series resistance to actually emulate the signal output, the supply output impedance, we can actually do that. So this is a simple circuit, a window based or a Schmitt Trigger based comparator circuit which is simulated in LTspice. Please post if you have any questions. You can easily implement this in your circuit where you want two different thresholds, and your circuit has to behave based on those thresholds. Thank you.